Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello friends. In this video, we are going to study the interfacing of 8086 microprocessor with 8087 math coprocessor. We will study that how the 8087 coprocessor interact with the 8086, the host microprocessor. So let's start with our topic. The 8087 is the first coprocessor developed by the Intel to pair with the microprocessor family 8086 and 8088. So why there is a need to develop a coprocessor? Because these microprocessors 8086 and 8088, they are not able to perform very complex arithmetic calculations, and also those calculations which involve very large numbers and very small numbers. So all these types of calculations, to solve them, there is the Intel, it developed a coprocessor 8087 which can handle such type of calculations very easily and very fast. So 8087 coprocessor, it provides very high speed calculations of the complex arithmetic problems. So the 8087, because it can solve the mathematical computations and mathematical problems 100 times faster than the 8086 and 8088 microprocessors. So that is an advantage, that if the microprocessor is solving any complex calculation, that will be solved by the coprocessor 8087, and meanwhile the microprocessor, it can solve or it can do some other task. So the CPU, the CPU working, that will be reduced, because the CPU of the microprocessor, it is not free from these complex calculations. It can now do some other tasks. Storage is also available, space is available, and now these complex tasks are performed by the coprocessor 8087. So that is an advantage of developing the coprocessors, that the main microprocessor is free from all these tasks, and all that tasks are performed at very high speed by the coprocessors. So the 8087, it is not the main processor, it is just a coprocessor, and it works in association with the host processors, that is 8086 and 8088. So 8086 and 88, they are called the host microprocessors. And 8087, because it is working in association with the main processor, so it is called the coprocessor. It also works in the same way, just like microprocessor is working, but it is not serving as a main processor. So that is why it is called a coprocessor. Now, just like the microprocessor is having its own architecture, its own instruction sets, just like that, the 8087 is also having its own architecture and its own instruction set. Okay, so we can say that 8087 is itself a processor which is having its own architecture and its own instruction set. Okay, now how when the 8086 and 8087 they are communicating with each other or they are interfaced with each other, how the instructions are executed. The main difference between the instructions of 8086 and 8087 is that in 8087 all the instructions they are having the prefix escape. Okay, so 8087 instructions they have a prefix escape. Okay, now whenever any instruction is given to 8086 and 8087, what this configuration is going to do, the just like 8086 microprocessor, we know that in 8086 there is an instruction queue in which 6 instructions at a time are fetched by the processor, and one by one these instructions will be decoded and executed by the processor. Okay, so when any instruction is written in the memory, then 8086 and 8087, just like the 8086 put the instructions in the instruction queue, 8087 it also puts the instruction in its own instruction queue. So both of them will have their individual instruction queue. Now, as I have said, the difference between the instructions of 86 and 87 is that 87 instructions they have a prefix escape. Okay, now in the instruction queue, when the 8086 finds that while decoding the instruction, it finds that the instruction is having the prefix escape, so it will treat that instruction as the NOP instruction, and that instruction is now executed by the 8087. So 8087 will do the decoding and then execution of that instruction. Now if the instruction is not having the prefix escape, then 8087 will treat that instruction as the NOP instruction, and 8086 is going to decode and execute that instruction. Okay, so we can say that the instructions of 8086 are treated as NOP instruction by the 8087. NOP means no operation. That means this processor is going to perform no operation at when this instruction is executed. Okay, and similarly the instructions of 8087 they are treated as NOP instructions by 8086. So each processor is going to decode the instructions which are there in its instruction queue and which are related to it, and the remaining instructions of the other processor they will be treated as the NOP instructions. So when an instruction is written in the memory, that instruction will be put in the instruction queue of 8086 as well as in the instruction queue of 8087. Both the processors they are going to decode all the instructions in the fetched instruction byte. That means all the instructions in the instruction queue, but they are going to execute only their own instruction. If they are encountering any instruction of the other processor, they will treat it as the NOP instruction. Okay, so 8086 will have its own instruction queue, 8087 will have its own instruction queue. If in that instruction queue any instruction of 8086 is there, so it will treat it as NOP instruction. In 8086 instruction queue, if there is any instruction of 8087, then it will treat it as NOP instruction. So this is how the main processor 8086 and 8087, they differentiate between their instructions. Okay. Now let us see the interfacing, that how the 8086 microprocessor and 8087 coprocessor, they interface with each other. Interface is the communication path between two components, okay, and interfacing is the technique that how these two components are connected with each other. So here we will study the interfacing, that how the 8086 and 8087, they are connected with each other. So 8087, it is connected as a coprocessor to the 8086. 8086 will work as the host processor or the main processor, and 8087 will work as the coprocessor. Now the 8087 is going to use the buses and the clock signals of the 8086 for its communication. So 8087, it uses input-output system, bus system, clock inputs of 8086. Okay. Now memory of 8086 is also used. Okay, not only the input-output system, bus system, memory and clock inputs, all of 8086 are used by the 8087. Now, when the 8087 is connected with 8086, in this microprocessor, there is a pin called MN, MX pin. That is, the 8086, it can operate in two modes, which are called the maximum and the minimum mode. And how these modes are selected? These modes are selected by the pin MN, MX pin. When this pin is high, then minimum mode is selected. And when this pin is low, then maximum mode is selected. So 8086 can operate in two different modes. Now when 8087 is connected with 8086, it operates in the maximum mode. Okay, means that this pin MX pin, this pin is low. Okay, so this is the main point to be remembered, that when the 8086, it communicates with the 8087, it operates in the maximum mode and this pin is at low value. Now let's see the circuit diagram, that how the 8086 and 8087, they are interfaced with each other. These are the connections for the interfacing. You can see that in the middle we are having the processor 8088 and 8086. This is the host microprocessor. Okay. Then 8087, this is the coprocessor. Apart from these two, this is the microprocessor, or we can say that host microprocessor, and 8087, this is the coprocessor. So apart from these two, there are other ICs also in this diagram. Here you can see that we are having 8284, which is going to provide the clock, reset and the ready signals. Okay, means the common signals which are to be provided to 8086 and 8087. These common signals are provided by the 8284. Then we are having the 8259, which is the programmable interrupt controller. So this interrupt controller is going to provide the interrupt from 8087 to 8086. Okay, it is connected to both of these. It is getting the input from 8087 and providing the output to 8086. Then we are having 8288. This 8288 is going to generate the control signals by getting the input status lines from the microprocessor. You can see that from the 8086, the status lines, that is S2, S1 and S0, they are given as an input to 8288, and this 8288 is generating the control signals available at the control bus. Okay. Then we are having the bus interface components also here. Bus interface components means that you can see that the address lines and the data bus, they are multiplexed with each other. So to separate them out, we are having the bus interface units, or we are having here an 8286 IC, which is going to latch the data from the address lines. Okay. So you can see that when the microprocessor is interfaced with the coprocessor, then we are requiring other additional components also for their communication, like 8284, 8259, 8288, 8286. So let's see that what these ICs do. (8086) or 8088, it is working as the host microprocessor. 8087 is working as the coprocessor. Then 8284, it provides the clock, ready and reset signals. Then 8282 used to latch the address, means to separate the address and data from the multiplexed lines. Then we are having 8288, which generate control signals. From status lines. Then 8259, which is the programmable interrupt controller. It accepts interrupt from 8087 and send it to 8086. Okay, so whenever we study the interfacing, we will see that in that connections we are having these following ICs. Okay. Now this configuration or this connection of 8087 with 8086 is called the coprocessor configuration, because the 8087 is not serving as the host or the main processor, but it is serving as a coprocessor. So that is why this whole configuration is called the coprocessor configuration. Now, as I have said that whenever the instructions are written in the memory, how the 8086 and 8087 they deal with it. So let's study this in detail, that how the instructions are executed. First of all, whenever we write any program, we write the program in the memory. So that program is an homogeneous program. Homogeneous program means that it contains the instructions of both 8086 as well as 8087. So first of all, a homogeneous program is written in memory by the user. This homogeneous program is going to contain 8086 plus 87 instructions. Okay. Now, one by one, all these instructions will be executed. The instructions which are written in the program, they will be executed. And we know that the instructions of 87, they contain the prefix escape. Okay. Now this escape is having the opcode 11011. Okay, so whenever the instruction, because first the instruction is going to be fetched and put in the instruction queue. So if the instruction is having the opcode, the starting opcode as 11011, then the processor will get to know that it is an 8087 instruction. So 8086 will treat it as the NOP instruction, and then 87 will execute it. So when an instruction is means first instruction is fetched. Okay, now microprocessor is getting to know that it is having the prefix escape, so immediately 8087 will come into action and then it is going to execute that instruction. Now if that 8087 instruction is only having the opcode, no operand is present. Okay, like it is not requiring any operand, only opcode is required. Operand is implicit in the instruction itself. Okay, so if the instruction is having no operand, then 8087, it does not require any data. Okay, so 8087 will start the execution of that instruction and 8086 will immediately move to its next instruction. Okay, suppose that this is the program in which many instructions are written. Now first instruction, it is having the prefix escape, and suppose that any instruction is written after it. So escape is means that it is the 8087 instruction. So 8086 is not going to execute it. It will treat it as NOP instruction. 8087, because this instruction is not having any operand, so just the execution is to be done. So 8087 will do the execution and 8086 will go to the next instruction. Okay, so in this way the instruction which is having no operand, that will be executed. Now if the instruction requires an operand, okay, so that operand is available in the memory and 8087 is using the memory of the microprocessor 8086. Okay, so how that instruction will be executed? Now, if the instruction is requiring any operand, that operand is to be provided by the memory. Okay, so the 8087, because it is using the memory of the 8086, so it cannot calculate the physical address. Okay, it is unable to find out that at what location in the memory that operand is available. So it needs the help of the microprocessor. So what the 8086 is going to do, the 8086 microprocessor, it will take the first word of the operand. Okay, because we know that operand, it will consist of the bytes. Okay, so starting first word of the operand, that will be taken by the 8086 to calculate the physical address of the operand, that in the memory what is the location of the operand. Okay, and after calculating that physical address, the that physical address will be available to 8087, so that 8087 can pick the operand from that memory location. Okay, so first word of the operand will be used by 8086 to calculate the physical address. Okay, so after getting the address from the 8086, the remaining words, they can be fetched by 8087 by simply incrementing the address of the first word. First word is given to 8086. 8086 has calculated the physical address, so first location is available to the 8087. Now remaining words, they will be available to the 8087 simply by incrementing the address of the first word. Okay, so in this way the 8087, it will start the execution of the instruction which requires a memory operand. So any instruction, either it will require the memory operand or it will not require the operand. If it is not requiring the operand, 8087 will simply do the execution. If it is requiring the operand, then it will take the help of 8086. Now, when it is executing the instruction, the 8087, it makes its busy line high. In 8087, there is a pin called busy pin. Okay, busy line is there. So when this line is made high, it means that 8087 is busy in executing the instruction. So this busy line is connected with the test pin. This busy pin of 8087 is connected with the test pin of 8086. So when this pin is high, the 8086 will get to know from the test pin that 8087 is busy in executing the instructions. So 8086 will now come to the next instruction. So when this busy line is high, and because this busy line is connected with the test pin of 8086, so 8086 will get to know that 8087 is busy in executing the instructions, and then it will go to the next instruction and start executing it. So in this way, when one instruction is being executed by 8087, 8086 has jumped to the next instruction. So this provides a multiprocessing. Because you can see that the instructions are executed by 8087, at the same time 8086 is also executing the instructions. Now during the execution of the instruction, if 8087 it requires the read and the write cycles, it required to use the cycles or the buses of 8086, then it will use the request and the grant pins. So when the 8087 is doing the execution of the instruction, during that execution, if it requires to read and write more words from the memory, then it will do that by stealing the bus cycles of 8086. Now how this stealing is done? It is going to send in 8087, there are two pins called the request and the grant pins, RQ0, GT0 and RQ1 and GT1. These are the two request and the grant pins of 8087, which are also connected with the request and the grant pins of 8086. Okay, these are the common pins. So when the 8087 it requires the use of the bus cycles of 8086, it will give an active low signal at this pin. So 8087 will send an active low request pulse to 8086. Now at that time 8086 will be doing some work. Okay, some task will be done by the 8086. So 8086 will complete the execution of the current cycle, and after that it will give the grant signal to 8087 that it has released the control of its bus cycles, and now the buses can be used by the 8087. So 8087 gives the request signal to 8086. 8086 completes its current execution, it completes the bus cycle and then gives the grant signal to 8087 that it has released its control. Now 8087 can use its bus cycle. Okay, so in this way the 8087 and 87 is using the buses of 8086 and it is completing the execution of the instruction. Now when the 8087 is doing the execution and using the cycles or buses of the 8086, after it has completed the execution of the instruction, it will give back the control to 8086 by giving a release pulse to the 8086. Okay, so first request is given, buses are under control of 8087, it has used the system buses, it has shared the system buses with 8086, and after that it has again given back the control to 8086. Okay, so in this way the complete communication between the 86 and 87 it is completed. Now when an instruction is executed by 8087, it will give the result of that instruction. Now this result is to be provided to 8086. How this result is given to 86? Now whenever 8086 requires the result of the 8087 operations, then it will first execute the wait instruction. What this wait instruction does, it checks the test pin. As I have told that this test pin is connected with the busy pin of 8087. Test pin is of 8086, busy pin of 8087. So if this busy pin is high, okay, then test pin is also high. So 8086 will get to know that right now at this moment 8087 is busy. So it has to wait for some time. Okay. So when this pin is high, busy pin is high, then 8086 enters wait state. When this pin is low, means test pin is low. It means busy pin is also low. It means that 8087 has finished its execution and now the 8086 get result of 8087. So whenever 8086 requires the result of 8087 operation, it will first execute wait instruction. Wait instruction is going to check whether the test pin is high or low. If it is high, then 8086 will enter the wait state. It will wait for the time when this busy pin will become low. Now when this busy pin is low or the test pin is low, then the 8086 will get the result of an 8087 operation. So you have seen here that how the instructions are executed by the 8087 and 8086 configuration. When they are in the coprocessor configuration, that how the instructions are executed, how they share the bus cycles, how they will differentiate that this is the 8086 instruction or 87 instructions, and how the results are displayed. Okay. Now during an execution, if any exception or an interrupt is occurring, then how that interrupt will be handled? Let's see. Now in 8087, the exceptions or the errors, they can cause an interrupt to the microprocessor. So during the execution of an instruction, if any exception or error is occurring which is unmasked, okay, unmasked means that that error is going to occur. Masked means that that error is not going to occur. Okay, masking and unmasking. So if the error is unmasked, then 8087 is going to interrupt the microprocessor 86 using the INT pin through the programmable interrupt controller 8259. You can see in the diagram that we were having 8259 PIC here, and from 8087 we are having the INT pin. This INT pin is given to the controller, this interrupt controller, and 8259 is connected to the interrupt request pin of the microprocessor. So whenever any exception is occurring, this pin is activated and this pin will be activated. So an interrupt is given to the microprocessor whenever any error or any exception is occurring in the 8087. Now, because as I have said that 8086 is also having its own instruction queue and 87 is also having its own instruction queue. Now whenever 8087 coprocessor, it wants to know that what is the status of the instruction queue of 8086, then it will use the queue status lines QS0 and QS1. These are the queue status lines, and these lines will give an information to 8087 that what is the current status of the instruction queue of 8086 microprocessor. These lines will have different values like 00, 01, 10 and 11. 00 means there is no operation. 01 means so these two lines are used by 8087 to monitor the queue of 8086 so that it can synchronize with the working of the microprocessor, that what is the status of the queue of 8086. According to that, it is going to synchronize its own queue. Okay, let's see how. If it is 00, then no operation will be done by 87. If it is 01, then 8087 is going to compare the 5 MSB bits with 11011, okay, to check that whether it is an 87 instruction or not. This is for the SK. If it is 10, then 8087 it clears the queue. If it is 11, then if the above comparison succeeds, then 87 is going to fetch the subsequent byte, else it is a no operation. So in this way, the 87 is going to synchronize its own queue, its working with the microprocessor. Okay. So we have seen the interfacing of 8087 with 8086, that how they are connected with each other, how the different components in different ICs they interact with them, and what is the role of these ICs we have also seen. And this is the complete interprocessor configuration of 8086 and 87 to form a homogeneous system. You have seen that 8288 it is providing the control signals, 8259 it is the interrupt controller, 8284 it is providing the common signals, and this is the bus interface components. Okay, so the complete that how they are executing the instructions, how they are synchronizing with each other, we have seen that at every step how 8087 uses the cycles and uses the 8086 for its working. Okay, so this completes the interfacing of 8087 with the microprocessor 8086. I hope that this topic is now clear to you. Thank you.